Hi everyone, welcome back to Stats. So last week we talked about chi-square analyses, which is when you have all discrete variables. Now we're going to be starting to talk about what you do if you're analyzing data where at least one of the variables is on a continuum from low to high scores. And so we're going to be talking about how you compare two means. So for this week, we're going to be talking about z-tests and t-tests. And for this first video, we're going to be going over how to do z-tests. So sometimes I might accidentally call it a z-test. If I do that, it means exactly the same thing as a z-test. That's just because I've taught a lot of stats classes in Canada and they say z instead of z. It's not some fancy other analysis, so you don't have to worry about that. When you're doing z-tests and t-tests, this is where you have two separate groups or two separate sets of observations, and you're seeing if the means are statistically significantly different from each other, or if they're about the same as each other, or not significantly different, in which case that would support the null hypothesis that those two means are the same. So the z-test is something that is actually not used very much. So in the textbook, the author talked about how you really only see z-tests talked about in Intro to Statistics textbooks. This is in part because there aren't very realistic assumptions about when you would use the z-test. So you use a z-test when you know a lot of information about the population. Specifically, you know what the population mean is, so what the average is for all the possibilities for that variable out there. So for example, if you were looking at, say, introversion in the United States, you'd have to know the average level of introversion for every single person in the United States. Another thing is that you'd have to know the exact standard deviation. So the exact variability of the variable, in this case, introversion, in the population. And usually we don't have that much information. That's why we're collecting samples in the first place, because we don't know everything about the population. But z-test is a lot more straightforward in terms of running statistically. So we usually start talking about z-tests, and then we get into t-tests, which are used a lot. We're going to be going through a lot of different types of analyses. So it's going to feel like this huge long list of z-test analyses, and then when we get to t-tests, it's going to feel like, am I going to have to memorize, 20 different ways to do t-tests? Fortunately, you don't. I'm not going to expect you to memorize how to run all of these individually. I definitely do not have them memorized. And essentially what we're going to be doing is we're going to be looking at what assumptions are met for our data, which assumptions are not met, and then based on which assumptions are met and not met, we're going to be running different types of analyses, essentially. So we do a lot of research in psychology where we're interested in comparing different means. So especially you're going to see t-tests all the time in research. So for example, if you're looking at whether the mean for your sample is below or above the national average for grades, you could do a z-test for that if you know the mean and standard deviations for all the school districts, or you could use a t-test if you didn't. You also might be interested in the outcomes of a clinical trial. And so if you're comparing an experimental condition to a control condition, this is another instance where you would want to do a t-test. And obviously we do a lot of clinical trials, and just generally we do a ton of experimental research in psychology, where we're comparing an experimental condition where we're manipulating something to a control condition where we don't do that. You also might be interested in if there are group differences. So you might be comparing income between men and women and seeing how big is that difference, and is that difference statistically significant? And you also might be looking at how things differ before or after a specific event. So there was a lot of research that happened in psychology, for instance, looking at psychological outcomes before 9/11 happened and after 9/11 happened to see if there were changes in, say, anxiety or people's mood or susceptibility to different disorders. So this is, again, where you're comparing the mean before something happened to the mean after it happened. So this is something that is very basic, but it's very valuable. And if you do research in psychology, I pretty much guarantee that you will be using t-tests. So with that, let's jump into examples of how to run z-tests in R. One thing I will say is that there isn't actually a great way to run z-tests in R in the same way that there is for most of the other analyses that we'll be doing in this class, just because it isn't used very much at all. So people don't really make functions and packages for z-tests. But with that saying, let's jump into this example. This is where we're going to be looking at grades and if they differ from the population mean. So it's basically looking at, do psychology students' grades in a class differ from other majors? So I'm going to load up this data set, zepo.rdata, and let's look at grades here. So you see there's a list of grades that psychology majors got. And with that, we can calculate the mean for our sample. So the mean for the entire sample is 72.3. And remember that we get that by adding up all the scores and then dividing by how many scores there were. So we can compare this to the population mean. And so what we know from the data that were provided was that the mean grade for this class is 67.5. So this is an instance where this professor has all of the grades for every student that has taken this class. So we know what the actual population average is if we're only trying to generalize to that specific professor's specific class. You know, 67.5 is lower than 72.3. So at a glance, you can see that the mean is higher just descriptively, but then we want to see if that's a statistically significant difference or not. And that's when we can use a z-test. For this, we're going to want to put in the sample mean for grades. And so I'll run this and we'll see that now, rather than just printing that out, we've calculated that out and saved that as sample.mean. Then what you're going to want to do is use the null hypothesis comparison. So in this case, mu refers to the population mean. So mu null basically means the population mean. It's kind of a short way of saying that. You could call this, of course, anything you'd want to, but again, it's good to give meaningful names to these variables. So we now have a score 67.5, and we're comparing that to 72.3. And the actual standard deviation for the whole population is 9.5. So this is imagining that, again, we have all of the scores for every student that's ever taken the class, and we know that the standard deviation is 9.5. So we're just putting that up there. Then what we need to know is the sample size. And you'll remember that the length function tells you how many data points there are in a vector. So it's going to look at grades and see, okay, there are 20 grades in this sample. And then we could print that out, and you could see down here that that value is 20. All right. So what we're going to do is we're going to take the standard deviation and divide that by the square root of sample size. And what this is going to give us is what's referred to as the standard error of the mean. And you remember that that is essentially the standard deviation for if you took populations with a size of 20. And so the idea is if you took random samples of 20 from that population where the mean is 67.5 and the standard deviation is 9.5, how much variability would there be in the means for that population? So we'll calculate this out, and then what we're going to do is use that value. So you're seeing that the standard error of the mean is 2.124265, so a little bit higher than 2. So basically what that means is that if you think about 95% of the distribution being within about 2 standard deviations, roughly what that means is that if you go about 4 or 5 below 67.5 and 4 or 5 above 67.5, 95% of the time your samples of 20 are going to be within that range just by random chance. So then we have kind of that critical range where if the mean is well above that or well below that, that is statistically significant. If it's not, then it's not going to be statistically significant. So now we're going to get the z-score for this. And what the z-score is going to be is it's going to be the mean for the sample and the mean for the entire population. And this is going to be divided by the standard error of the mean. And so this is going to tell us how many standard errors that population is below the sample in this case. So if you actually subtracted the scores, you'll remember 67.5, 72.3, that is 4.8. And then we're dividing it by the standard error of the mean, which is 2.12. And basically what you're seeing is that the mean for psychology students is 2.259606 standard errors above that mean. So that's pretty far above what we would usually expect. Again, usually about 95% of the distribution is within 2 standard deviations. So this is a little bit above that. And so what we can do here is that we can look at the upper range that we would expect just by random chance. And so here we're putting in the upper range if there is a normal distribution, which again, standard error of the mean, sampling from a population is normally distributed. So when we run this, what we get here is that that upper area, which is beyond 2.259606 or higher, is only a little over 1% of the total distribution we would expect by chance. So it's basically just right at the border of being in the top 1% of means that we would expect to sample by random chance. So then when we're using p-values, we're imagining that we're using a two-tailed test. So then what we're doing here is we're also getting the lower area here as well. And what you'll see is that this is actually going to be exactly the same. So this is imagining that we're looking at scores below negative 2.259606, so on the other extreme end of that normal distribution. And then for this, we're going to be adding that up, and this is how we get the p-value for a z-test. And so for this, we're adding up the lower area, so the lower extreme, so as extreme as the score but in the opposite direction, to as extreme as this score or higher in the direction that we looked at it. And then this gives us the actual p-value for the z-score. So the p-value here is 0.023-84578, and that is less than 0.05, which is usually the alpha level that we have, or the cutoff for p-values that we use. And so we would look at this p-value being less than 0.05, and we would be able to conclude that the psychology students scored higher than the mean for everyone that has ever taken the class. So that sounds good for the psychology students. They seem to do a bit better on average. So of course, this is just a little bit below 0.05. So it's not that unlikely this could be due to random chance. So in other words, we had just enough power to be able to detect this if this is the real difference here. So again, when we're doing the z-test, we have to be able to know the mean in the population. We have to know the mean, the standard deviation of the population as well. And we're also assuming that the standard deviation for the sample that we have is also the same as the population. So again, making a lot of assumptions to be able to run this z-test, and then we can even calculate it out ourselves without much work. But because we usually can't do that, that's why we usually do t-tests. And that's what I'm going to jump into in the next video. So I'll see you there.